Hi everyone. Today we're going to be modeling tangent planes and normal lines with an example. I have here my beautiful girlfriend. Get PDA nerds. Calculus nerds can still be Rizzy. So, we're going to be dealing with this example here. This is specifically a two-sheet hyperboloid. And we're asked to find a tangent plane at point 132 along with a normal to that point on that plane. So here's what the function looks like if you're curious. It's just a regular two-sheet hyperboloid, plus or minus 2 on each side. And we're asked to find the point of 1, 3, 2. So what is the tangent plane at this point? That is what we are trying to find. So let's go ahead and do that. So we're going to pretend that this is a 4D function. And to do so, we're going to call this for let's say like a W as a placeholder, dummy variable, so that this whole thing becomes a level curve. Okay, so we're taking this 3D two-sheet hyperboloid function, we're turning into a 4D thing, and this will represent a level curve. So let's call a function of x, y, z equal to negative x squared plus y squared minus z squared. So if you plugged in 1, 3, 2, you would get out 4 here. Okay, so let's use the gradient here to find a normal to this level curve, right? Because we're now saying that this is a level curve at this point that will be at a height of 4, but it's a 4D function. So let's find a normal to that by taking the gradient. So the gradient of f, and we're going to take partial of x plus partial of y plus partial of z. So we're going to get negative 2x, that will be I, right? That unit vector, plus 2yj minus 2z, and then that's going to be the k unit vector. Okay, so that's the gradient. And remember how we define a plane, right? If I have, if I want to find a plane, I need a point, okay, and I need a normal. So let's say this is the normal to a plane, right? We're just defining this to be some normal, and we have a point. Using this, we can use a formula, and we'll find a normal. Sorry, my drawing's kind of bad, but just imagine that's a flat plane. So we just need a point here on that plane and then the normal to it. We know that the gradient on that level curve is specifically that normal vector, and we also have a point. So let's evaluate the gradient at this point to find the normal at that specific point, because this function just tells you at any point. So we're going to plug in, I'll just plug everything in a while, but it's going to be negative 2. 2 times 3, that's going to be 6. Negative 2, 6, and then we plug in a 2 here, that's going to be negative 4. Okay, so negative 2, 6, and negative 4 is going to be that normal vector to our point. And to define a plane, we just say A, x minus x naught plus B, y minus y naught plus C z minus z naught. So, and that's all going to be equal to 0. So that defines a plane. Remember, this is the dot product of a normal with a line on that plane. Okay, so there's a normal, there's a line. If they're mutually orthogonal, sorry, not mutually, if they're orthogonal to each other, then they'll produce a plane. So this is how we find that. And when you solve everything out, it's going to be, I have it in my notes here. So see if you can get the same thing as me. So x minus 3y plus 2z equals negative 4. That's what you should have gotten. So let's plug in everything and try to understand what this actually looks like. So we have our point. And now let's plot, and this is in Desmos, so if you want to follow along, you can. Let's plot our vector for that normal. So if you type in vector and you put it as an ordered pair from one point to another, you can find that normal. So if we put in 1, 3, 2, and then we put in the terminal point of our gradient evaluated at 1, 3, 2, we're going to get negative 2, 6, negative 4. And if you look at how this points, if I just quickly remove the curve, I got to zoom out a little bit, it looks kind of like this. And it's probably not obvious what it's pointing to yet, but I can go ahead and just quickly visualize. Let's put in a point 0, 2, 0. Okay, so this is going to be at the top of this graph. And let's also put in x equals 0. Okay, so remember that the gradient tells you if I go this way, I'm going to reach the top of at that specific point. The gradient at a specific point tells you the way of which you can move to ascend a curve the quickest. And you can see our vector, right, this red vector from our point 1, 3, 2 is pointing to the center of that 2-sheet hyperboloid. Okay, so hopefully it's pretty obvious that that is the steepest way of ascent, right? So this all works out, and it points as such. So let's put in our tangent plane now to show the tangent plane at that point. So we assign the normal and we explain, we visualize kind of how that normal looks. Now let's put in a plane. So all we have to do is type in our plane, x minus 3y plus 2z equals negative 4. And let's call this plane a different color, right? It's kind of hard to see. So let's give it a nice orange color. And let's remove all the background noise. Okay, so this plane contains the point 1, 3, 2. And if we look at, how it's intersecting this 2-sheet hyperboloid, you can see it's just touching at one singular point, thus defining it as a tangent plane. So you could do this with any point on this curve, right? You could put a point. Let me think of one. 2, 7, 3. Is that contained on the cone? It's close, not quite, but let's say you pick any other point, it could work. So I just wanted to visualize today, if we put it all together, kind of what these tangent plane normal line math looks like in Desmos. And you can do this using the same kind of methodology. So hope you enjoyed. Bye-bye.